Hello. Welcome. Hello, everybody. It is now mid-September, which means it is now winter in Ohio. It's a joke, but really, it's cold. And it's cold in my office, too, because I was too lazy to turn the heat back on. So, cold all over. Welcome to the beginning of the network layer. But first, let's answer the unanswered questions from the Wireshark lab. And I think you have until tonight to finish it, so I'll just roughly answer those few questions that were left over there. Well, first, the bonus question that I asked at the end last time was, what's a probe? Right, so the probe has a pretty funny payload. A probe is something that typically the router will send on another user's behalf to see if anybody is currently at a particular IP address. So typically, the router will send those out to see if anybody's using it. So it's a ARP request where we don't expect a reply. We expect there to be nobody who has that IP address. And if nobody has it, then somebody else can claim it. So that's a probe. Now, where we left off, I think we had just finished the gratuitous ARP or announcement. And I think we were on the specific ARPs to a particular device. So we said that these were for refreshing the ARP table. So device 1 wants to refresh their entry for device 2, which might be expiring soon. So they send one specifically to device 2 to ask them to confirm that they're still where they're at and they're still online. So very similar to a probe, only here you would expect a response. What happens if some machine on the network intercepts every ARP request for what's supposed to be your address and claims that it's theirs, right, and assume that yours reply faster than theirs do? This is basically ARP spoofing. In that case, you would get all the traffic intended for the victim, and they would be booted off the network because they wouldn't be able to claim an IP, so they wouldn't be able to get any traffic to them. So this is one way of kicking people off a network by sending a gratuitous amount of ARP spoofs. Usually there's not much traffic to be stolen in this manner, so it's not great for intercepting traffic intended for the victim, but it is a great way to get them booted off the network. So, fun way to get people booted off the network, but you need to be able to craft link layer packets to do so. Hopefully we'll get around to that towards the end of the semester. What happens if you change your device's MAC address? Would you stay connected? This is MAC spoofing. Sometimes people change their MAC address for a number of reasons. The easiest is you got banned from the network, or in a very rare case, somehow it ended up that you have two devices with the same MAC, which shouldn't happen. But as we slowly run out of MACs, that could happen more often, lazy manufacturers. It should also be noted that MACs technically have a recycle date. Once a device was manufactured, let's say 15 years ago, it's pretty reasonable for the manufacturer to say, well, we'll just reuse that one. So for example, Apple doesn't support iPhones 4 and below anymore at all, I imagine. So the 4 and below MAC addresses might start being recycled at some point. Who knows? There hasn't really been an official mechanism for doing that. But if you change your MAC address, it's like you are a whole new device. You are connecting to the network fresh. You've got to send a new gratuitous ARP to get your stuff back. You would probably need to get a new IP and everything too, though, because it would be like you were all new to the network. So say you have a server at 555 that occasionally goes down, and you have another identical server. You want it to be able to take that one's place. So the first layer of this is you need to be able to tell when it goes down. So based on what we learned, you could tell when it goes down by having 555, that guy, constantly send you traffic over the link layer. That's going to require you to have your own MAC. And when that traffic stops, you assume that they've gone down. That'd be one way to do it. You could also do it by ARP requests and replies. You could send them a request. They can send you a reply. But you need some way to see when they go down, which means polling them periodically to see if they are up or not. So Once they've gone down, how do you take their place completely? Well, you would have to spoof your MAC address to be theirs, so it would appear as if you were that machine, and then you could simply take over their traffic. You would probably need to send another gratuitous ARP out in order to update everybody's switch tables, so you would be connected on different ports probably, maybe to the same switch, maybe to different ones. But there would be some confusion after that first spoof, as traffic would try to be forwarded to the now dead port. So you would need to send at least a gratuitous ARP, update everybody's switch tables and stuff. And that's basically it. That's how you would take over. This was a not very commonly used trick, but something that is sometimes used in IT to have a failover really fast. So you can do this, but it's certainly not standard to do this as your failover mechanism. All right, if any other questions on the lab, put them in chat. Otherwise, I think we covered everything. I guess one thing I want to point out, we talked about the gratuitous ARPs and the announcements. I did say they are the same, and that's basically true, but some people differentiate a gratuitous from an announcement, in that an announcement is when you first connect to a network, and a gratuitous is just any time you send a gratuitous ARP. So just something to keep in mind. They are pretty much the same in structure. Sometimes different implementations will change the opcode depending on whether it's the first time they've sent it or it's a gratuitous ARP down the road. But none of that really matters to you. That's IT stuff. Someone asked, what happens if two devices on the network have the same MAC? That's bad juju, because then link layer traffic can't get to either of those. They'll just randomly either get traffic intended for the other one, or neither of them will get anything, because no one will be able to properly update their switch and routing and switch and ARP tables. They'll keep getting confused. It'll say, well, wait, you're supposed to be at 11111, but someone else here with the same MAC as you says they're at 22222. It would be as if, to everybody else, as if you were taking the same machine, but you kept switching what port it was on, so they would just get conflicting ARPs and conflicting entries in switch tables. Those two devices probably wouldn't be able to properly get traffic on the network. So one of the reasons that some high-end server equipment gives you the ability to spoof MAC is to avoid that situation, or I don't know, for other IT reasons. There are legitimate reasons to spoof your MAC occasionally, outside of avoiding a network level ban or something like that. One nice trick you can do, by the way, if you're lazy IT for cybersecurity, is that if you have a network that's comprised entirely of company-owned devices, you can make it so that only devices with a particular MAC manufacturer MAC ID are able to connect to your network. That is an easy way to stop outside attackers, or at least to slow them down slightly, because they would need to figure that out, and it's not really intuitively obvious. The problem is that, as some of you might have noticed, you might have a Dell computer or a Lenovo or something else, but your NIC is manufactured by a completely different company, and sometimes even within the same model and brand, your NIC will be manufactured by completely different companies. One computer gets a Broadcom, one gets an Intel. It just depends on what off-the-shelf NIC was cheaper that day. So it's a very hard policy to put into play. And with that, let's get started on the network layer. The network layer. Layer 3, so 2 knocked out. Now we're on the 3rd, the network layer. This is one of the most complex and also quite relevant to you as developers, so we're going to spend a few days on it today, and then 2 or 3 more beyond that before we move to the transport layer, which will be our final layer before we start getting into fun application development and cybersec stuff. And hopefully there will be some cybersec stuff along the way here as well. So remember again that all of what we're talking about goes in that payload. No way around that. The frame is the smallest unit of transmission, so think of the frame as an envelope with a header on it. Everything gets stuffed in that envelope, and we're going to see that then stuff gets stuffed inside another envelope in there, and so forth. It's stuffing all the way down, payloads all the way down. Now, all the services that we got at the link layer are guaranteed. Remember, we got error checking, right? We got physical addressing. There are some other things guaranteed at the physical layer, like that you won't break the other person's NIC when you try to transmit to them. They sync up with the preamble and all that good stuff. Okay, so the hero of the network layer is the mighty router. Incidentally, this is also the router I recommend if you're looking for a router. This is the TP-Link 1750. If you need the, if you have a big house, get the 90 series. If you have a 3,000 square feet or less, get the, I think it's the 70 series. These are definitely the cheapest in their performance class, and they are very good routers all around. And you can install DDWrt on them almost universally, which is great. Some people don't recommend them because they're of Chinese manufacture. I think that's a big plus, because I don't care if the Chinese spy on me. They can see anything they want. I don't live in China. Haha. Okay, so the TP-Link and the router. Now, most people are familiar with this kind of device as a router. This is actually many devices in one. This, you see, has antenna, so it's actually a Wi-Fi hub. It's also a router, and then it is also a switch. So it has all the different types of things in there. So router is just one of this particular device's duties. Some people also have router modem combines. That means they're probably Wi-Fi hubs, routers, switches, and also modems. All right, so as network parts get cheaper, more common to see those combo units. Most customers don't want multiple things on their table, so these combo units are very popular. There was a time when your Wi-Fi hub was more likely to be individual, its own little piece of equipment. So the network layer, unlike the link layer, which connected physical devices on the same network, the network layer primarily connects different routers together. So we can say that it connects different LANs together. And the connection of different LANs together is what comprises the internet as a whole. So the internet is just made up of many different routers connected to one another. That's the internet, essentially. So routers connect LANs, and they do so over the network layer. Now, you might say that when two routers are talking, so two routers that are physically connected are talking, you might call that still the link layer, and to an extent that's accurate. So you could call it the link layer or the network layer, I guess, even though typically routers will only talk over the network layer. But connection between distant routers, routers that aren't physically connected, is definitely a network layer thing. And what routers are generally facilitating is the communication of distant devices, devices that are far from each other's LANs. So let's look at a very simplified map. So in here, the circles with the X's on them are routers, and the squares with the X's on them are switches. So let me point your attention first down here to enterprise network. They have their router, right? And then they have a switch, and then they have their wireless hub. So this is a pretty old school picture, right? That's pretty rare for you to have a standalone wireless hub that connects to your switch. Not very popular. And then on this home network, they've got the router connected to a, again, wireless hub directly. So for the home network, right? And then these guys here, these strange looking things with buttons, are the modems for these folks. Now, what you might consider is that these two devices, as they're pictured, might again just be bundled into one device today. So that's just one device today. So this picture is an abstraction. This line between them is really talking more about the digital hardware that connects them internally than treating them like two different devices. So something to think about. All right, and the picture here kind of shows you that they all communicate over the network layer. So if this router wants to talk to this router or this router over here, but more importantly, if this computer wants to talk to this computer over here, their traffic has to go over a series of routers in order to reach that destination. And that's why we call them routers, because they route traffic to where it needs to go. So if you're on enterprise network over here and you need to talk to mobile network, all you do is send your traffic to your router, give it the destination IP, and it will figure it out eventually. It will get to where it is going. Also, notice that there's lots of different kinds of tech that are pictured here. Again, physical layer stuff. These guys obviously have something over their line. They have a modem that they need to use to connect to the internet. These guys over here on their phone are using a cellular tower to connect to the internet. The cellular tower still connects to a router, still connects to the national network, the local or regional network, etc. Yeah, and then the enterprise, they're pictured as not having these fancy phone lines, which means they probably have what? Fiber, right? They probably have fiber. So they're using the same connection that's between all the different backbone units. So these connections, all you were probably thinking, are fiber, right? Everything here is probably fiber. All right, so key differences from the link layer. We're obviously not directly connected to all of our neighbors. We don't have access to their physical address. So if you were thinking of addressing in terms of the real world, the physical address would not be like your house's address. The physical address would be more like, my house is the third one on the right when you turn into my street. That kind of description is useless unless you're in physical proximity, right? It does not help anyone to send you a letter. Okay, so like my house is the red house, my house is the one built by this company, my house is the third house on the right. Those are all physical layer descriptions that are really useful for routing people to your house when they're already near it. But if you wanted to send somebody a letter, you would use a more formal addressing system. And also on that physical description, only one house on the street should match that physical description at a time. Otherwise, those directions are useless. So again, very similar to Mac. But in this case, we need an address. We are not broadcasting traffic. We are sending it to a specific place. We want our traffic to arrive at a particular address, 123 Main Street or whatever. So IP addresses are much closer to the formal kind of home addressing that you're probably used to in the real world. So the network's key functions are to forward traffic to the next leg in the journey. So the router obviously doesn't get the packet all the way there. The router only sends the packet onto its next step. So a series of forwards will eventually get you to where you're going, but every individual router only knows the next step, only knows where to send your packet next. And that plays into routing as well. Routing is determining which path is best. So there are multiple different ports on a router, and the router might have many different choices of where to forward your packet. Routing is deciding which direction to forward your packet so that it gets there best, or gets there at all, really, because routing is complicated. Just the fact that your packets arrive at all is pretty miraculous, right? So routing is figuring out the next step to get there, and forwarding is passing it along to the next leg in the journey. So every router builds a routing/forwarding table. If you took 328 with me, you'll remember having to do some Digistraka's graph theory networking stuff. And yeah, I know that's not how you pronounce his name. It's Distraka, but come on, it's spelled that way. And these Digistraka tables are a lot like how routers build their routing and forwarding tables. They use very different methods, obviously. They don't do an exhaustive search to find the best path. But the concept is similar, that you're trying to find the best path between two connected nodes on a very, very complicated graph, a graph of billions of devices around the world. So if you haven't done that yet, hopefully you do that in 328. Graph theory is a jolly good time. You might think about how it works in the real world, because it is tremendously complicated. We might get into it at some point, but it's more an IT thing, so we might not. Technically, a router stores a forwarding table, and what we talked about in 328 is technically a forwarding table. It doesn't know the whole journey, it only knows the next hop. So a routing table technically is the whole journey. If you only know the next leg in the destination, it should be called a forwarding table, but that doesn't matter. If you say forwarding or routing table, everyone will know what you mean. Those are both kind of synonymous in common parlance. A forwarding table maps the final destination, or at least a portion of the final destination, to the next hop. So if a letter is addressed to Ohio, you know that it needs to go to this post office next in order to make it to its final hop. You don't need to know which post office it finally ends up with or anything like that. You only need to know where it goes next in order to facilitate its transmission. So let's look at some examples of routing / forwarding table, whatever you want to call it. So here we have a bunch of different nodes connected, A, B, C, D, E. Okay, and A's routing table, obviously A goes to itself. It's local, so itself. To get to D, how do you go? Well, you would go south, right here. Great. That gets you to D. To get to B, you go east. That gets you to B. How about to get to C? C is over here. So the fastest way to get to C is via B. Go east. Okay? And then B will figure out how to forward your traffic the rest of the way. So notice the rest of the journey is not listed here. All you know is that to get to C, I need to send my traffic to B, and then B will figure it out the rest of the way. Likewise, to get to E, I could actually go either of these two directions. So this is where routing comes into play. These would, assuming that they are the same cost, assuming that link is the same latency and everything, I could go either to B or to D. So here I have to make a determination of routing. And normally you would do that based on the cost of those links. But to get to E, you go through B. And you can look through this table some more, see if you can figure out all those other fun links. In practice, they look more like this. You've got a bunch of IP addresses. You've got a bunch of subnet masks. We'll learn about those in a bit. And then it tells you which gateway you are going through and which physical port attached to your router that corresponds to. That would be more like what a routing table looks like. If you've ever worked in IT, you might have dumped these on a router that was misbehaving. Generally, though, these things are populated automatically. Most people are too afraid to touch them because it's very, very complicated. So some extra forwarding terms we might not have covered. Routers will examine the header of the IP address to determine where to forward. And we'll see in a bit that IPs are divided into subnet masks, which makes it easier to forward. This is how the forwarding is typically accomplished. It's also why MAC addresses aren't suitable for this kind of addressing. Anything that forwards traffic is typically called a packet switching device. So if you take a packet and then you retransmit the same packet further along, you are a packet switching device. If you are a packet switching device on the link layer, you're called a switch. If you're the same thing on the network layer, you're called a router. So it depends what tech you use. But again, remember that the network layer runs on the link layer. So technically both are also link layer. So network layer devices all have an IP address. It's 4 bytes long, but typically expressed rather than being expressed in hex, it's expressed in regular old base 10 digits. I don't know why this is. I don't know why MAC addresses were addressed in hex, while IP addresses are traditionally expressed in digits. I speculate it's because a lot of regular old people have to use IP addresses once in a while, and obviously regular people are uncomfortable with hex, so I think they just decided to go ahead and make them base 10. Likewise, for IT people, it just makes it easier, I guess, although I figure almost every IT person knows how to use hex as well, so again, not really sure. But of course, each byte can be 0 to 255, which leaves us how many for the entire world? Not nearly enough, right? So we ran out of IPv4 addresses ages ago, and now we use all kinds of interesting mechanisms in order to make the best of the few that we have left. And also, because of the mistakes made in the 70s, the biggest mistake being using only 4 bytes for the address, we now have IPv6, which has significantly more bytes for the address and allows us to never run out again, hopefully, unless we expand across the whole galaxy, because that's how big IPv6 is. We'll look at that probably in a couple of days. So 4 bytes, not very many devices, and many are reserved. Why not just use the MAC? Why not just use the lovely 6-byte MAC address for all network layer duties? At some point, it was speculated that we might. These technologies sort of grew up next to each other. Remember that there are other technologies besides Ethernet. They just all eventually got outcompeted. Likewise for IP, there were other technologies besides IP. They all just got outcompeted. And that's pretty much the way it is. That there's really no practical reason why the Mac didn't have the same kind of addressing that IP does. It just so happens that those two systems had their own sort of different intended goals, and Mac ended up not being suitable for forwarding because it doesn't have any way to group them, which means there's no proper way to route them. We'll look at how IP is grouped in a bit, but Macs are grouped just by manufacturer, and of course, anything made by Apple, the iPhones are spread all around the world, right? They're not clustered in any way, so it would be impossible to use Macs for routing and forwarding. You would have to have a routing table with literally every device in it, and that would be impossible. So because the Mac wasn't set up for that kind of forwarding, we needed another tech. That ended up being Internet Protocol, IP, and here we are today. So back to routers. Routers have several input ports and several output ports, but traditionally your home router will just have one input port connected to the outside internet. It'll come from your modem. And then a switch is a little bit different. It has no in-out traffic between different machines, and it doesn't have this concept of an outside LAN. To a switch, everybody is both an input and an output. It's just a bunch of different devices connected together. A router has this technology inside of it called the switching fabric that binds input ports and output ports. Complicated computer engineering stuff, complicated computer hardware. And a router also has its own processor, so a router is actually a small computer of its own, and a rather strong one compared to other embedded or small devices. The router's processor does a lot of work. It builds routes, plans routes, builds forwarding tables, and switches and forwards all of your traffic as well. So the router is quite smart compared to, let's say, the switch, for example, which just has minimal processing power. The routers also run some kind of pretty sophisticated firmware usually that allows you to log in and change settings and do all this different kind of stuff. You can flash DD work done there and log in and change even more settings and do even more stuff. So the biggest goal of the router is obviously to introduce as little time overhead as possible. You want to switch as quickly as possible. In fact, ideally, you want to be able to start retransmitting a packet before you've even finished receiving it. Think about how that's possible. So remember, the header comes in first on the wire. Things are physically transmitted at much slower than the speed of light over those twisted pair Ethernet cables. As soon as the header starts coming in, as soon as you finish reading the header, you might already be able to figure out how to forward a packet. That would be ideal. Okay, so if price permits, that is if the price of memory permits, routers will generate the forwarding table and store multiple copies. And ideally, again, you can finish the lookup in your forwarding table using the header before the whole packet is even received. So that's an almost zero latency switching. But the delay that the router incurs is the delay between the receiving of the first byte of that packet and then how long it takes it to start transmitting the first byte of that packet. That is the delay the router incurs. So there's no such thing as instant forwarding. You need to read at least the header, but the header can be as small as maybe 100 bytes, and that means that you can forward very, very quickly. So what kind of data structure should a forwarding table have? Should it be, for those of you who took 328, a tree, a hash map, a linked list? So traditionally it was a tree. You had your different destinations as different nodes in a tree. So you would read the IP address in sort of tree form to determine which port to go to. In modern times, hash maps are obviously much more favored. So you'll typically see hash maps or their similar ilk used instead, and there are other expensive, complicated math tricks involving additional physical memory and other kinds of stuff that you can do in order to make the forwarding tables even more efficient, make that lookup even faster. So people are always prioritizing how to make the lookup of where something needs to be forwarded as quickly as possible. Let's look a little bit at how you would physically switch traffic. So you have inputs on your left, 0, 1, 2, 3, 4. So assume this router has 4 inputs, 4 outputs. At the top you have your outputs, 0, 1, 2, 3, 4. One way to do it is a crossbar switch like this, where there are a bunch of physical interconnects, and if you want to route traffic, for example, between input 1 and output 0, you would have to turn this and this switch on. So all of these little squares here pictured can be turned on or off. So 1 can talk to 0. The advantage of a crossbar switch is while 1 is talking to 0, 2 can also talk to 2, for example. These can both be on at the same time in some configurations of crossbar switch, or 3 can talk to 3. But if 3 is talking to 1, then it's hard for 2 to talk to 2 because it crosses over the same switch that's being used by 3 talking to 1. So this obviously becomes very complicated. You need a fancy microcontroller to make this work, as well as a bunch of different switches and all this wonderful stuff. It's definitely a complicated way to do it. There's also many other physical switch types besides the crossbar. So just keep in mind that it's real complicated in there. The switching fabric is a very complicated thing. But also it's not that simple, right? It's not just traffic in is traffic out. There are speeds and bandwidths to consider. You might not necessarily be able to send at the same rate you receive, or vice versa, or you might get a huge load of traffic to send, and it might take you a while to figure out where to route it, and so forth. So at every port, both input and output ports, pictured as blank boxes here, there's also a memory buffer. So there's also a little unit of memory, a little memory chip that stores the incoming traffic. And then at the output, there's the same, a memory buffer to store the outgoing traffic. And these are a few different other topologies here, a memory and a bus, and again the crossbar there. So the red-lined areas pictured here are buffers where the traffic waits while it's either waiting on something to open up in the switching fabric. So maybe the switching fabric is busy, you want to transmit from B to Z, you have to wait for the crossbar to open up. Maybe you can't send as quickly as you can receive. All kinds of different reasons why packets might be caught waiting in the router. And obviously the more buffer you can afford, the better your router. What happens when your buffer is full? Let's see if anyone can answer that in chat. What happens when a packet arrives at the input and the input buffer is full, or a packet is queued to be sent and the output buffer is full? What happens to that packet? Someone asked if crossbar is the most efficient. I don't know. It's a computer engineering, very complicated question, all the efficiencies and everything of the different arrangements. I'm sure they all have their own pros and cons. Mostly comes down to cost. Whichever packet switching fabric is the optimal one is probably not optimal for the money. And most consumer routers are under $100. So you're looking at something where people are pretty price sensitive already. So I'm not sure which is the best, and I'm certainly not sure which is the best for the money. But what happens when the buffer is full? The packet goes bye-bye, or someone has to go bye-bye. Somebody has to be discarded, and that's bad. And again, in this picture, remember, typically only one packet gets to move through the switching fabric at once, unless you have some kind of configuration where, like here, B can talk to X because they happen to not cross each other. So obviously the router has to be able to hold multiple packets in those buffers at the input and output. The act of holding them before sending them is called buffering usually, and the act of ordering them within that buffer is called queuing. So who gets to go first once the transmissions start flowing again, that's queuing. So the simplest way to queue, obviously, is just in the order that things arrive, like we typically queue in line, but there are other ways to queue beyond that. So consider that you have 3 input ports and they are all receiving traffic destined for one output port, and assume everybody has the same speed. All the ports have the same speed in this case. Now, those 3 input ports can do a number of things. They could each take turns sending one packet, We could wait until one is completely done transmitting and then let the next guy go. There's a lot of different approaches to make it happen, right? So there's no correct answer there either. And then how much buffer do we need at the inputs? Also a complicated question. It depends on how much traffic we get. In this case, we probably need at least 3 times more than the output buffer in order to avoid dropping anything. What happens to packets that arrive and the buffer is full? Again, they just get discarded, or that also depends on your queuing system. Maybe the packet that arrives is a higher priority and someone else who is already in the buffer gets discarded. So 3 inputs, 1 output. If the output buffer gets exceeded, some packets get dropped. You can just keep them in the input buffer until they're ready to go in that case. So how much buffer do you typically get in your router? It depends again on your price. Typical, simple, standard is your bandwidth times the round trip time. That should be about how much buffer you should have. So if you have gigabit internet and 250 millisecond ping, or round trip time, then you should have about a quarter of a gigabit worth of buffer, which isn't that much memory in terms of money. It probably only costs a few dollars at the manufacturer's end at most. So what are some methods for dropping packets that arrive when the buffer is full? The simplest is drop tail, drop the last to arrive, so last in the queue. There's random early detection. This is an interesting and also very simple method, but it allows you to not drop a bunch at once. It allows you to drop them in a more staggered way. So with random early detection, once you get past, let's say, 50% of your buffer being full, you start dropping with, let's say, 10% probability any packet that arrives. As you get closer to full, your probability gets closer and closer to 100% of a drop. The disadvantage to this system is obviously that if you got to that 50% full mark and started probabilistically dropping packets, but you actually would have never reached a full buffer in the first place, then you just drop packets for nothing. So this is helpful to stagger the lost packets, but then unhelpful in the sense that you are dropping packets when you don't absolutely need to. And then the most complicated method is to actively manage the queue in some way, to drop in according to some rules. And dropping in accordance to some rules is overhead, right? That makes the router have to do more processing work. So there's buffers on both ends, remember, at the input and the output. Input queues are generally waiting for the switching fabric to open up. So while the switching fabric is busy, things sit in their input queues, whereas the output queues are waiting for the physical transmission medium to open up, or for the packet to just simply be transferred just because of speed. It takes time to transfer a packet. Even when it's in that output buffer, it doesn't just go all at once. It goes 1 bit at a time, just like everything else does. And remember that the switching fabric typically only moves 1 packet at a time. So the conclusions for you in development land are that your traffic has a lot of different things that it depends on in terms of how long it's going to take to arrive where it's going. And not the least of those is whether or not the routers along the way are busy. And here we have an example of something called head-of-line blocking. Input 1 and input 3 both want to transmit to 4. So I got the red lines showing that they want to go to 4. But the switching fabric can only move 1 at a time. There are other packets queued up for 3 and for the other packets queued up at 1 and 3. So these guys here, the 321 and the 213, 134 here, are also waiting for these guys to be sent. So these guys are at the front of the input buffer, so they're next ready to be sent. But this is a switching fabric that can handle, let's say, moving between different inputs and outputs at the same time. So actually one of these guys could send to 4, while this guy, for example, transmits to 3 and just skips over the one at 4. So these inputs are being delayed needlessly in this situation, unless the router can figure it out and quickly open up the switching fabric to transmit to 3. Open this guy's up to transmit to 3. So just another one of those examples of how routing, even at the switching fabric level, is very hard. Determining what order that packets get queued in is usually called packet scheduling. So the queuing synonymous with packet scheduling. The most typical scheme, as you would expect, is just first come, first served. But even routers that just do first come, first served will typically have priority exemptions. And that means something that just gets to jump to the top of the queue. Advanced scheduling can actually slow down your switching or actually cost more money. Let's think about why that is. If anyone has an answer, post in the chat. Why is something more complicated than first come, first served either going to add cost or potentially make it worse? Now, hold on. I thought all traffic was supposed to be neutral, or at least it was, then it wasn't again, then it was again, then it wasn't again. And very back and forth on net neutrality. So what does neutrality mean in the context of packet switching? Let's say Time Warner decides that your League of Legends and Netflix packets get to wait. They get to the back of the queue, or they get less priority than, say, Hulu traffic, because all the cable companies are partners of Hulu. So Hulu gets to go to the front, Netflix gets to go to the back. That would be wrong, obviously. But Netflix, which is not time sensitive, should definitely get a lower priority because it's not time sensitive. So my voice coming in on YouTube here and my video also probably don't need to be prioritized, because if this video lags an extra second or two, nobody cares. But your voice coming in on Discord needs to get top priority, right? Because if your voice lags there, you're going to have a really bad experience. And that's actually what's done in practice. So pure net neutrality, giving each packet the same priority, would be a disaster. It needs to be that certain traffic gets lower priority over others. So bulk downloads, things that are not latency sensitive, get queued at a lower priority than things that are latency sensitive, like voice chats and games and video chats and all these other different things. Yes, someone asks, is this similar to the quality of service on your LAN? This is a big part of quality of service. Scheduling is probably the largest factor in quality of service. So let's look at some of the priorities that IEEE created for what kind of traffic gets to go when, or what kind of priority traffic gets. Not everybody follows this. It's up to ISPs how they want to do their prioritization and everything on their own. So the internet service provider can do whatever they actually want to do on their own network. Essentially, I don't think there's any legal requirements for them to prioritize in a certain way. The lowest priority is background traffic, and then the next priority is best effort. So something like a download would probably be considered a best effort packet. You don't need to try too hard to get it there. It's just the best effort. Then there's excellent effort, critical applications. Don't know what they mean by critical applications. Then video. So video is one of the highest priorities. This is live video, so probably not something like YouTube. Maybe YouTube Live could be considered in this category, but video is one of the highest priorities. Then voice, with a 10 times better standard. So video should arrive within 100 milliseconds. Voice should arrive within 10 millisecond latency with 10 millisecond jitter. Jitter is your variance in latency. So voice has very high priority, the highest, and that's because when there's a delay, the human brain gets real confused. We don't like seeing delays in our conversation. Voice delays are the most noticeable to us. Video delays, generally we can sort of filter out, but voice delays are really noticeable to us. So typically, any kind of voice traffic should get top priority, otherwise the conversation seems really jarring. And you've probably noticed that if you've ever had like an international phone call or something where the delay is high on a normal basis, it becomes really jarring. It's also the same reason that Zoom meetings are so jarring, right? Because somebody starts talking at the same time as somebody else, it takes about 2 seconds to notice that you're talking simultaneously, and then you both have to back off and decide whose turn it is. That doesn't happen much in real life, right? That latency makes it difficult for our communication systems to run. And then the highest levels of priority are network controls. Okay, so these always get high priority on every network. The packets that tell routers what to do or populate routing tables and do all this stuff, those come in at max priority. They always jump the queue, and they're usually small, so they always get transmitted. They generally never get dropped. All the network controls need to come through to keep the network running. Now, this doesn't really apply as much to fiber backbones. And the reason why is simply because fiber usually isn't that saturated. And fiber is so fast anyway that the queuing of all of this stuff actually would add more overhead than uh, than just sending everything at the same priority, because fiber is generally so fast that the queuing, the couple milliseconds or microseconds you spend on queuing creates more overhead than just transmitting everything. And here we'll look at for mobile for LTE. This generally is in use, or something similar is in use by all the mobile service providers. Again, the top priority, they inverted the order, so the top one is at the bottom, is it? Yeah. Okay, the top one's at the bottom still. The most important one's at the bottom still. It's hard to read this thing. Okay, anyway. Different priorities. I don't even think they're ordered. I think they're just loosely ordered. But the one with the least delay, the one that's the highest priority over LTE, is real-time gaming. Hooray! Yeah, obviously real-time gaming needs low levels of latency. Non-conversational video, like streaming, so like what you're watching right now on YouTube, has one of the lowest priorities, 300 milliseconds of delay allocated for it. Conversational voice is pretty tight at 100, as well as voice and video live streaming and interactive gaming down here as well. So interactive gaming differs from real-time gaming. It has lower latency requirements. And then video buffering and then TCP-based traffic. We'll learn about TCP much later, such as sending emails, point-to-point file sharing, those kinds of things. Those also have one of the lowest latency requirements. So what happens if you run some kind of service that masks all your traffic as TCP? Well, you would get downgraded to the lowest level of latency. But then there's also the error loss rate here, something else to consider. So certain kinds of traffic have a tighter tolerance for time, but then a lower tolerance for lost traffic. So for real-time gaming, the tolerance is one of the lowest, because lost traffic in gaming, not that big a deal. You send a lot of packets, you'll just get another relatively soon. Whereas lost traffic in voice, kind of a big deal, because you'll lose a piece of the audio there. And lost traffic in file transfers, a very big deal, because then you have to retransmit that packet again, but at the same time, not a very big deal, because you can retransmit it again. Anyway, something to consider. Lots of different prioritizations. These all factor into what is called quality of service. The scheduling and everything factors into what's called quality of service. What you just looked at are basically quality of service tables, offering different quality of service guarantees for all those different kinds of traffic. Packet scheduling is probably the largest component in quality of service, but it's not the only factor. There are other things as well. So routers have a lot of work to do. Okay, so what do we call the packet, the unit of data at the network layer? So we called it a frame, remember, back in the link layer. So here we call it a datagram. Something on the network layer is typically called a datagram. So we have frames at the link layer and now datagrams at the network layer. And there are two major kinds of datagrams. Two major kinds of datagrams using Internet Protocol or IP technology. Again, there were once other competitors to IP. Today there are essentially none. In Wireshark, I might ask you again to try to find something that's not IP. And again, you will probably be hard-pressed to do it unless you're on a very particular kind of network. So they're typically called IPv4 and IPv6 for short. We're going to primarily be discussing IPv4 because all the addresses are shorter. That's really the only reason we discuss 4 instead of 6. Most people would know what you meant if you said IP packet instead of datagram. I think actually most people wouldn't know what you meant if you said its formal name, which is datagram. So IP packet is probably the better term when you're talking to people in IT or something. Don't say datagram. No one knows what a datagram is, except software developers. So you'll know what a datagram is. And IP generally is synonymous with network layer, just because IP is the pervasive network layer protocol. So again, network layer. Typically, there are actually other approaches, but IP and network layer are usually just synonyms, just because of how much IP dominates the network layer. just like how Ethernet dominates the link layer. So we'll just briefly glance at the header before we call it a day for today, and then we'll look at it in some more detail next time. So this is the IPv4 datagram. All of this lovely stuff at the top is, of course, the header again, and then you've got your payload or your data, which is of varying sizes. So we'll see that this header is much bigger than Ethernet's. It's got a lot more information packed in there. And it's 20 bytes big if you don't have any options. So there's an options field comes before the data, and that has variable length, which we'll see later ended up being a really dumb decision to have that. But 20 bytes, a lot of overhead here. Anyone remember how long the Ethernet frame header was? How long was the Ethernet frame header? At a certain point, once we've learned about all these different layers, I'll ask you to compute the total amount of header overhead. So something to keep in mind. All right, your homework is due this evening. I'll post another homework later today. It will probably involve some network layer stuff too. So if you want to hold off for a bit until we've covered it, you can. But I think that everything that's assigned to you, you should be able to look up just based on what we've covered today. You don't actually need any additional knowledge to do the homework. So if you want to get started right off, you probably can. All right, that's it for today. Thanks for tuning in, guys. I will see you on Friday.